halogen atom will be replaced and in place of halogen atom, a nucleophile will be substituted. That is called as nucleophilic substitution reaction. The mechanism takes place in two steps. First, carbocation will be formed, then the nucleophile attaches and you will get the product. Now, we are superimposing these means. That is, we are keeping one on top of another means it will look exactly the same. The mirror images of that will look the same. So, that is chiral and achiral. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry. So today we are back with session 4 of the chapter Haloalkanes and Haloarenes. So in the last session, we discussed about the physical properties of haloalkanes, right, as well as chemical properties of haloalkanes. The various chemical reactions of haloalkanes were discussed in last session. So we begin with the nucleophilic substitution reaction, right? Okay, it's not just the one reaction, there are other reactions as well. So first we started with the nucleophilic substitution reaction, right? So in detail we are going to study about two ways in which this nucleophilic substitution reaction can take place and the mechanism of that. That means how exactly stepwise the substitution is taking place we are going to study in this session. So one method is substitution nucleophilic unimolecular SN1. What does that mean? We will discuss in detail in this session. Then substitution nucleophilic bimolecular SN2 reaction and stereochemical aspects of nucleophilic substitution reaction. SN1 mechanism in optically active alkyl halides, SN2 mechanism in optically active alkyl halides, as well as order of reactivity of various alkyl halides in SN1 and SN2 reactions. So all of this we are going to discuss in this session. So as I said, we have already discussed what is nucleophilic substitution reaction, right? So, which chapter we are studying? Haloalkanes and haloarenes. So, what did we discuss? Halogen atom will be replaced and in place of halogen atom, a nucleophile will be substituted. That is called as nucleophilic substitution reaction. So, this can happen in two different ways. One is SN1 mechanism and another one is SN2. So, let's see. Nucleophilic reactions has been found to proceed by two different mechanisms. First one is substitution nucleophilic unimolecular, that is SN1. So, what does the S stands for? Substitution. N stands for nucleophilic and this 1 stands for unimolecular. Also, we can say that the kinetics or the order of the reaction is 1. We have studied chemical kinetics chapter, right? In there we have studied what is order. So, the 1 stands for unimolecular, or else we can also say that it is a first order reaction, right? Okay. Now, next one is substitution nucleophilic bimolecular, SN2. So, again here S stands for substitution, N stands for nucleophilic, 2 stands for bimolecular, or the order will be 2. That is it. It is a second order reaction. So, in detail, let us begin with the SN1 reaction and the mechanism in detail. Let us understand. Okay. So, again, SN1 stands for substitution nucleophilic and it is unimolecular. Okay. So, SN1 reactions are generally carried out in polar protic solvents. Now, what is polar protic solvents? So, polar protic solvents are solvents which has the ability to release H plus ions, okay? So, in such conditions, SN1 mechanism will take place. So, water, alcohol, acetic acid, all these are examples of protic solvents. They can release H plus, right? So, another important point to remember is it is a two-step process. So, this mechanism or this SN1 mechanism takes place in 2 steps. Okay, in detail we are going to study that. So, that 1 stands for unimolecular, but the reaction takes place in 2 steps. Okay, like this you have to remember that 1 stands for unimolecular, reaction will take place in 2 steps. Okay, so example we are going to take here and let us understand the reaction what is taking place. So, tertiary butyl bromide undergoes hydrolysis with aqueous KOH to form tertiary butyl alcohol by SN1 mechanism. So, you can see here this is 2-bromo, 2-methyl propane, that is the IUPAC name. You can also call it as tertiary butyl bromide. So, this is how it is, CH3, you have another CH3, you have another CH3, and you have Br, which is your halogen. Okay, and we are undergoing it hydrolysis in the presence of aqueous KOH. So aqueous KOH we are using means which will be the nucleophile. It is OH minus. In detail we have studied it in the last session, which are the nucleophiles for various reagents, right? So OH minus will be the reagent. So when it undergoes hydrolysis, what happens? We are studying nucleophilic substitution, right? So this OH minus will attach here and the Br will be, that is the bromine will be replaced, right? So substitution will take place. In place of bromine, OH minus will be substituted. So what you are going to get? CH3, CH3, CH3 and OH will be attached here, substituted, and Br minus will be replaced, right? So this is how you are going to get. So that is 2-methyl propane 2-ol. Okay. So this is the reaction which takes place. Instead of Br, you are going to get OH there. Okay. So now we are going to study in detail about the mechanism of it. Okay. So what is the first step? What does the first step happen? As I said, this is a 2-step reaction. So these 2 steps are very, very important. This SN1 and SN2 mechanism is really important for your examination as well. Okay. So what's the first step? The haloalkane undergoes slow ionization to form a carbocation and a halide ion. So the first step is the formation of a carbocation. So how it is formed? As you can see here, the tertiary butyl bromide that we have discussed here. Now what happens? Comparing carbon and bromine, which is more electronegative? Bromine is more electronegative. Hence, what happens? This shared pair of electron will have a tendency to be attracted more towards this bromine. So what happens? The bromine will be taking up this electron, right? One extra electron which is shared between carbon and bromine, and the bromine will leave with that electron and form Br minus. It will be removed from the compound, right? Now what will happen? Once this bond is broken, that electron is gone with the bromine. So what happens to the carbon? Carbon will have a positive charge. So the carbon having a positive charge, it is called as a carbocation, right? So that is the first step where there is a formation of carbocation. So the first step which is happening here, we have not mentioned that step, right? So the first step which is happening here is the formation of carbocation. How it is formed? By the leaving of the Br minus. Clear? Now the step 2 is nucleophilic OH minus attack. The nucleophile OH minus attacks the carbocation to form tertiary butyl alcohol. So now carbocation is formed. Now what is it we are discussing? Nucleophilic substitution, right? So the nucleophile is going to attack now. Right. Now, which is the nucleophile? We have taken KOH means which is the nucleophile? OH minus is the nucleophile, right? So, OH minus will attack the carbocation which is formed in the first step. Now, what happens? This will attack this carbocation. Okay, to this carbon which is having positive charge and this is having a negative charge. Now what happens? A bond will be formed here and you get a tertiary butyl alcohol. I hope it is clear, right? So the same thing that we have discussed now, in 2 steps this reaction is taking place when we are discussing the mechanism. First step, carbocation is formed. Then in the next step, the nucleophile will attach and form tertiary butyl alcohol. Okay, now the kinetics of the reaction. As I said, it is a first order reaction or it's a unimolecular reaction. Now, why is that? Let's see. In this type of reaction, the rate of the reaction depends only on the concentration of haloalkane and it is independent of the concentration of nucleophile. Okay, what does that mean? First step, what we are doing? Yes, you have the haloalkane, right? And then in the next step, the nucleophile comes into place. So, only the concentration of how much haloalkane we are taking, based on that, the reaction will proceed. Okay. So, when the more amount of haloalkane is taken, the reaction will proceed much faster. Okay. And it does not depend upon the concentration of the nucleophile which has been used. That is why the rate of the reaction will only depend upon the concentration of alkyl halide or concentration of haloalkane which is taken, right? So step 1 is the slowest step and hence it is the rate determining step. So this is also an important point to remember, right? This first step, that is the formation of carbocation. This is a very, very slow step. So whichever is the slow step, that will be the rate determining step of the reaction, right? So which is the rate determining step? The first step will be the rate determining step. In the step, only one reactant molecules take part. So it is a unimolecular reaction, right? Only haloalkane, one molecule of haloalkane is taking part in the reaction. Hence, it is a unimolecular reaction. So I hope SN1 is clear to you. So what and all we have discussed here? Yes, the mechanism takes place in two steps. First, carbocation will be formed, then the nucleophile attaches and you will get the product, right? And kinetics, it is a first order reaction. Only the concentration of alkyl halide is considered. There is no effect even if the concentration of the nucleophile is changed, right? And it is the first step, which is the formation of carbocation. It is the rate determining step, right? Now moving on to SN2, that is substitution, nucleophilic bimolecular reaction. Okay, it's a bimolecular reaction. So let's take an example and understand this. Hydrolysis of methyl chloride. When methyl chloride is heated with aqueous KOH solution, methyl alcohol is formed. So now we are taking methyl chloride here. There we have taken tertiary butyl chloride. We are taking methyl chloride. Okay, so what is methyl chloride? CH3Cl. And in presence of KOH, which is the nucleophile again, it will be OH minus. So what happens? OH minus will be substituted in place of Cl, right? So you will get CH3OH, which is alcohol, and you will have KCl. So this is the reaction which is taking place. Now in detail, we are going to discuss about that. So mechanism, this mechanism involves only one step. Okay, so this is important to remember. Please don't get confused. SN1 reaction take place in two steps. SN2 reaction take place in one step. Clear? That 1 and 2 which is mentioned here, right? This 1 and 2 stands for unimolecular and bimolecular. Okay. When the nucleophile OH minus attacks the carbon, it approaches the carbon atom only from the side opposite to the chlorine atom to form a new carbon OH bond. The formation of COH bond and the breakage of CCl bond takes place simultaneously. There exists a transition state in which both OH minus and Cl minus are partially bonded to the carbon atom, and COH bond becomes stronger and CCl bond weakens. So as discussed, this reaction, that is SN2 mechanism, is a single step reaction. So let's understand the mechanism, what is exactly written here. Using this example, let me help you to understand. So as you can see here, this is the CH3Cl which is being mentioned here, methyl chloride, and to this the nucleophile is attacking. Okay, so the nucleophile, as you can see, the halogen atom is present on the other side. Okay, and the nucleophile will be attacking onto the carbon atom. The carbon atom is present here, right? It will be attacking the carbon atom from the opposite side. As the Cl, that is a halogen, is already there, OH minus also cannot attack from that side, right? It will attack from the opposite side, and you will get a transition state. Okay, that is an intermediate state. This is a very short time, for a very short time only it will exist. It's a transition state. So in this transition state, you can see it is represented by dotted lines, right? So the halogen atom will be also there. The OH minus will be, that is your nucleophile, will be also attacking from this side. The halogen will be removed from the other side. So it is shown by a partial bond. That means this bond is being broken and this bond is being formed. So it's a transition state where all these 5 are existing. So carbon can only have 4 bonds, right? Carbon's valency is tetravalency, but as you can see now it is forming 5 bonds. Is it not? Is it possible? No, right? So this is a transition state wherein this bond is being broken. Carbon chlorine bond is being broken. Carbon OH bond is being formed, right? And finally what happens? This bond will be broken and Cl minus will be removed and OH will be formed here. So as you can see here, another point also. So as you can see here, the configuration also have changed. As you can see here, the 3 hydrogen atoms are towards this side. Now the OH minus is attacking from this side and the Cl is removed from the other side. Now you can see the configuration has changed to the other side. The 3 hydrogen atoms were in this side. There you can see it is in the other side. So there is an inversion of configuration also which is taking place, which we will discuss in detail. So I hope this is clear. In case of SN2 mechanism, it's a single step process. A transition state will be there where OH minus as well as Cl minus will be present. Then Cl minus will be removed and the alcohol will be formed. I hope it is clear. Now, as this happens, the configuration of carbon atom under attack inverts in much same way as an umbrella is turned inside out when caught in a strong wind while the leaving group is pushed away. This process is called as inversion of configuration. That is what I have discussed now. As you can see, all the three hydrogen atoms are towards this side. Now, when the nucleophile is attacking from this side, this is being removed, and what happens? These three hydrogen atoms will be towards the other direction, as you can see here, right? So, there is an inversion of configuration which is taking place in SN2 mechanism. It will not happen in SN1. Hence, finally, Cl minus gets completely detached to give the end product, which is methyl alcohol. Okay. Now, moving on to the kinetics of SN2 mechanism. This is a one-step reaction. Hence, the rate determining step involves two reactants, that is a molecule of alkyl halide and the nucleophile. Therefore, the reaction is bimolecular. As you can see here, both of these are involved as the reactants. In SN1, only the haloalkane was present in the first step, right? That is the rate determining step. Here, only one step is there in SN2. Hence, both of these are of importance. That is, the nucleophile as well as the methyl chloride concentration is important here. Okay. Hence, what happens? It is a bimolecular nucleophilic substitution reaction. Both are of importance. So, the rate will depend upon the concentration of alkyl halide as well as nucleophile. So, what will be the order of the reaction? The order of the reaction will be 2. So, it is a second order reaction and it is a bimolecular reaction because both of this concentration are taken into consideration. Okay. So, I hope this is clear. Now, moving on to the stereochemical aspects of nucleophilic substitution reactions. Stereochemical aspects. So, before moving on to the stereochemical aspects of it and the details in SN1 and SN2, what is happening? The inversion of configuration, there is retention, racemization, many things we are going to study. Before that, let's begin with the basics of the stereochemistry. Okay, there are some terms which we have to be clear with, then we'll move on with that. Okay, so some basic stereochemical principles and notations we are going to discuss. Okay, so first is optical isomerism. So you might be familiar with optical isomerism already. In class 11 itself you have studied what is geometrical isomerism and optical isomerism, right? So when two compounds, okay, there are two compounds which are having same molecular formula and same structural formula also. Molecular formula is same, their structure is also same. Then what is differing? They differ in the direction of rotation of the plane polarized light. They are said to exhibit optical isomerism. So, when plane polarized light, okay, when plane polarized light is passed through this compounds, what happens? It will rotate the plane polarized light either towards the right or towards the left. Based on that, we can say that they show optical isomerism. That is, they differ only in the direction of rotation. Either the plane polarized light which is passed through these two compounds, one will rotate that plane polarized light towards the right and another one will rotate it towards the left. So, only the direction of rotation of this light will be different. Other than that, their molecular formula and structural formula will be same. So, such a pair is called as optical isomers, right? Okay, let's see. The next part is optical activity. Now, what is optical activity? The property of a substance which makes it capable of rotating the plane of polarized light is called as optical activity. So, these compounds which have the ability to either rotate the plane polarized right towards the right or left, they should have that ability. Those compounds are said to show optical activity. Okay. Now, moving on to the next one, dextro and levorotatory compounds. So, the compounds which rotate the plane of polarized light to the right or clockwise are called as dextrorotatory and they can be mentioned as D or plus compounds. So, as I told you now, the plane polarized light, when it is passed through the compound, if the compound is rotating or the substance is rotating the plane polarized light towards the right or the clockwise direction, we call it as dextrorotatory. Okay, either it can be represented by the small letter D or with a plus sign. Okay, now the compounds which rotate the plane of polarized light to the left or anti-clockwise are called as levorotatory or L. Okay, if the plane polarized light is rotated towards the left, it is called as levorotatory, mentioned by L, or you can use minus sign also. Dextro D or plus, levo L or minus. Okay, asymmetric carbon or stereocenter. The next one is asymmetric carbon or stereocenter. Carbon atom with all four substituents attached attached to it are different. So there is a carbon atom, carbon's valency is 4, right? All the 4 bonds or the 4 groups which it is attached to should be different. Then we call it as an asymmetric carbon. So for example, let us take CH3, then you have C2H5 ethyl group, then you have a hydrogen, then you have a bromine. Okay, as you can see, it is an asymmetric carbon. All the 4 groups which is attached, you have an halogen group, you have a hydrogen, you have an ethyl group, you have a methyl group, all of it is different. So this is called as an asymmetric carbon. Now moving on to the next one, chiral. Now what is chiral and achiral? We are going to discuss. Now what is chiral? The objects which are non-superimposable on their mirror image are known as chiral, and the property is known as chirality. Okay, so if we take the example of our hand itself, so for example, if we take the mirror image of our hand, right hand, it will be our left hand, right? So what does superimposing means? If you are joining our hands like this, what happens? It will be on top of one and it will look exactly the same. But if you are taking the mirror image of our hand, that means right hand's mirror image will be your left hand, and we are keeping it on top of one another. That means superimposing. Okay. So on top of one another, if we are keeping, you can see my right thumb is on this side and my left thumb is on this side. So they are not exactly the same. If I am joining it like this, it will be same. But if I am keeping on top of one another, it is not the same. So if it is not same, they are called as chiral. Okay. And this property is called as chirality. As you can see here, a compound is shown here. See, CH3HOH and ethyl is attached. Here, the mirror image of that. Okay. The mirror image of that is shown here. And if you are keeping one on top of another, okay, one on top of another, what happens? Here the OH is on the other side, here the OH is on this side, here hydrogen is on the left side, here hydrogen is on the right side. Even these two are same, but what happens when we are superimposing, keeping it on top of another, what happens? This will be on the opposite side. Hence they are called as chiral. The carbon is a chiral carbon. Clear? Now what is achiral? The objects which are superimposable on their mirror images. Okay. So now these are substances which are superimposable on each other. That means if you keep one on top of another, they will look exactly the same. The mirror images of that. So you can see here CCH3, H and OH. The mirror image of that is shown here. Now we are superimposing these means, that is we are keeping one on top of another means it will look exactly the same. The mirror images of that will look the same. So that is chiral and achiral. Now moving on to the next one, enantiomers. This is very important. What are enantiomers? They are stereoisomers which are non-superimposable mirror images. They only differ with the respect to the rotation of the plane polarized light. If one of the enantiomer is dextrorotatory, the other one will be levorotatory. So already we have discussed when the plane polarized light is passed through the substance, if it rotates to the right, it is dextro. If it is rotated towards the left, it is levo. So this pair is called as an enantiomer. Okay, they will have the same molecular formula, structural formula, only in the rotation of the plane polarized light, there will be difference. One will be dextro and one will be levo. So this pair is called as an enantiomer. Enantiomers possess identical physical properties, melting point, boiling point, etc. will be same. So this pair of dextro-rotatory compound and levo-rotatory compound is called as an enantiomer. Now moving on to the next part, there are 3 outcomes for a reaction at an asymmetric carbon. Either it can undergo inversion, retention or racemization. Okay, if we have an asymmetric carbon, if it is undergoing substitution nucleophilic reaction, either it can undergo inversion, retention or racemization. So what is happening? Let us understand. Okay, first let us understand what is retention of configuration. Retention, that means it will remain same, right? So let us understand. During a reaction, if the reactant has same configuration of groups around the stereogenic carbon as that of the product, it is called as retention of configuration. So the example which is shown here in this junction, you can see that is your carbon atom, right? So to this carbon atom, you have an A attached, you have another carbon attached, you have an X attached, then you have a B attached. Now what happens? Y minus is the nucleophile that is going to attack here. Now what happens? Substitution will take place, right? X will be substituted by Y. And you can see here, the configuration is exactly same. Instead of X, Y has come here. That's it, right? B is still here, A is still here, C is still here. Their positions have not changed. Only X is being replaced by Y. That is the only change which is happening. So this is what we say, that the retention of configuration. Only substitution is taking place. There is no change in the position of any other atom. So this is called as retention of configuration. Next is inversion of configuration. So during a chemical reaction, if the product formed has opposite relative configuration as that of the reactant, then the phenomena is called inversion of configuration. So inversion of configuration example also we have discussed in SN2 mechanism, right? So if I am taking methyl chloride, okay, it is attacked by the nucleophile OH minus, so attack will take place from this side, okay, and what will happen finally, what I am going to get, CH3OH, that is alcohol plus Cl minus. So as you can see here, there is an inversion of configuration taking place. As you can see here, chlorine was here and the 3 hydrogen atoms were towards this side. So now you can see here from the other side as the OH minus has attached, what happened here, your alcohol will be formed, and on the other side you will have the 3 hydrogen atoms. So you can see from the diagram itself, it is on opposite side, right? There is an inversion of configuration which has taken place. So this is inversion. Now moving on to the next one, what is racemic mixture and racemization? A mixture containing 2 enantiomers in equal proportions which will have 0 optical rotation, as a rotation due to one isomer will be cancelled by the rotation due to the other isomer. Such a mixture is called racemic mixture or racemic modification. So what does that mean? As I told you, what is enantiomer? It's a pair in which one will rotate the plane polarized light towards the right, one will rotate it towards the left. So the pair which is present in equal amounts, if the dextro-rotatory and levo-rotatory, let's say for example 50-50% if it is present in equal amounts, what will happen? Yes, the racemic mixture will be formed, okay. It is a mixture containing 2 enantiomers in equal proportions, okay, and it will have 0 optical rotation. Why 0 optical rotation? One will be rotating it towards the right, another one will be rotating it towards the left. Means what? In total, the net effect will be 0, right? One is rotating towards the right, another one is rotating towards the left. So in effect, what happens? The net rotation will be 0, okay. So this is called as a racemic mixture, okay. So that is the D and L form in equal proportion. A racemic mixture is represented by the prefix DL. What does its DL stands for? D is dextro, L is levo, together, right? Or else you can represent it as plus and minus also, okay. Before the name, for example, plus minus butane 2-ol. This is a racemic mixture. The process of conversion of an enantiomer into a racemic mixture is called as racemization. Okay, so what is racemic mixture? It is clear. So this process of making a racemic mixture from its enantiomers is called as racemization. Right. Now, let us understand using a compound how inversion, retention and racemization is taking place in detail. Okay, so one example we have taken here. Okay, as you can see here on one, the carbon atom is present here. You have an ethyl group here, hydrogen here, X, which is to be substituted, and you have a methyl group here, to which a nucleophile Y is being added. Okay, nucleophile Y is added. So when A is being formed, so you can see this is one product A, one product B. So when A is formed, as you can see, there is a retention of configuration. Instead of X, Y is being substituted there. So all the other groups will be present in the same place, right? Their position has not changed. So this is example, or this is retention of configuration. Now here you can see instead of X, Y has been substituted, but the position of the other substituents has been inversed. Here it was towards the right side, here it is towards the left side. So this is the product B in which inversion has taken place. So here there is retention of configuration and here there is inversion of configuration. Here inversion has taken place, right? Now, as you can see, A plus B. Now, what is A plus B? Equal amounts of these two, A and B, if we are taking, it will be forming a racemic mixture. As you can see here, these two compounds, this B and A, which is formed, they are enantiomers, right? They are the mirror images of each other. If we superimpose it, they will not be superimposable. So, this is an enantiomer, which will be, that is, one is Da form, one is L form, and together you will get the racemic mixture, right? So A is the only compound obtained. The process is called retention of configuration. So if you are only getting A, right, that is retention of configuration is taking place. If you are only getting B, it is inversion of configuration. And if we take a 50-50 percentage, 50 percentage of both are being formed means racemic mixture will be formed and the product will be optically inactive, right? We have already discussed that. So I hope inversion, retention and racemization is clear for you. Right. Now moving on to the SN1 mechanism in optically active alkyl halides. So we are going to take optically active alkyl halides and we are going to discuss in terms of SN1 and SN2. We have studied what is inversion, retention and racemization. Which process is going to take place in SN1 and SN2 and the mechanism of that we are going to discuss now. Okay. So in SN1 reactions are accompanied by racemization. In SN1, racemization will take place. Actually, the carbocation formed in the slow step being sp2 hybridized is planar. The attack of the nucleophile may be accomplished from either side, resulting in a mixture of products, one having the same configuration as that of the alkyl halide and the other having the opposite configuration. So let us understand this paragraph which is written by this example itself. So you can see here the carbon is present here, methyl group is there, ethyl group is there and hydrogen is there. So now as we have already discussed in SN1 mechanism, what happens? Yes, nucleophile OH minus will be attacking here. It is a two-step process. We are considering the second step here, right? That is already the carbocation is formed here. Okay, carbocation is already formed here. Now, as you have all, we already know how to calculate the hybridization of this. So, this carbon atom will be having a sp2 hybridization, right? sp2 hybridization, what is the geometry? It will be a planar, right? Now, before forming the carbocation, it was, let's say, SCH3, C2, CH3, and you have hydrogen and you have this bromine. So in this case, it is sp3 hybridized, right? Why this carbon is sp3 hybridized? It is further attached to 4 other substituents. But once you get the carbocation, the hybridization will be sp2, right? sp2. Why only 3 other bonds it is forming, right? So this is sp2 hybridized carbon and the geometry will be planar. Hence what happens, as it is planar, the OH minus, that is a nucleophile which is going to attach, this can attack, see, as you can see the arrows, either it can attack from this side or else it can attack from this side as well. From either side, this OH minus, that is a nucleophile, can attach. So now if it is attacking from the right side, what happens? The OH will be attached towards the right side. And if it is attacking from the left side, what happens? Yes, the OH minus will be attached in the left side. So this is plus butane 2-ol. That is, this is your D form, that is dextrorotatory. Okay, and this is your minus butane 2-ol, that is levorotatory. So here what happens in either ways, that is from right side or left side, the attach of nucleophile can take place because your carbon is an sp2 hybridized carbon from either side, because it is planar, from either side it can happen. Hence what happens? Yes, D form will be formed, L form will be also formed, dextro as well as levo. Hence what happens? It will be present in equal amounts, hence racemic mixture will be formed. That is why we have written it is undergoing racemization. So SN1 reaction undergoes racemization. Clear? Now moving on to SN2. In case of optically active alkyl halides, the product formed as a result of SN2 mechanism has the inverted configuration. So in SN2, what you have to remember, inversion of configuration will take place. This is because the nucleophile attaches itself on the side opposite to the one where the halogen atom is present. So let's take an example here. This is the carbon atom. You have methyl hydrogen and C6H13 which is here. Okay. Now, what happens? SN2 mechanism. What happens? The bromide will be removed and the OH minus will be attacking here. That is what is happening, right? But how does this OH minus will attach? Will it attach from this side? No, it will attach from this side. That is OH minus will attack from the opposite side where the halogen atom is present. Okay. So, it will not attach from the forward direction, it will attach from the backward direction or the opposite direction. Hence what happens, as it is attaching in this direction it is attaching, there will be an inversion of configuration. That is what you can see, there will be an inversion of configuration and Br minus will be removed. So from the diagram itself you can see there is an inversion in configuration. So SN2 mechanism follows inversion of configuration, and in SN1 you will have retention of configuration as well as racemization which is taking place. right? Now, the order of reactivity of various alkyl halides, SN1 and SN2 reaction. So, you have primary alkyl halide, secondary alkyl halide, tertiary alkyl halide, right? Based on how many alkyl groups are attached in the carbon atom. Right. So, we are going to see what is the order of reactivity in SN1 and SN2, which one will show more reactivity. Okay. So, in case of alkyl halides, tertiary alkyl halide undergo SN1 reaction very fast because of the high stability of tertiary carbocation. So, in SN1 reaction, we have already studied that. Yes, it's a two-step process. First, carbocation will be formed. So, hence, in SN1 reaction, we are going to consider the terms with carbocation. So, we already know what is the order of stability of carbocation. Tertiary carbocation will be most stable, then secondary carbocation, then tertiary carbocation, right? So, in SN1 reaction, if we are considering, as tertiary carbocation is the highest stability, SN1 reaction, if we are considering, tertiary alkyl halide will undergo the reaction faster because tertiary carbocation is most stable. Because in SN1 reaction, carbocation is formed, right? Now, methyl halides react most rapidly in SN2 reaction because there are only 3 small hydrogen atoms. Tertiary halides are the least reactive because bulky groups hinder the approaching nucleophiles. Thus, the order of reactivity will be the opposite in case of SN2. So, in SN2, what we have discussed in SN2, it is a single step process, right? There is no carbocation formed here. So, in that case, it is easy when the number of alkyl group is less. Okay, methyl chloride we have taken as example, right? CH3Cl, and the nucleophile will attack from this side means, okay, we have studied there will be inversion of configuration. So, in this case, it will be easy because all the 3 are hydrogen atoms. But instead of one hydrogen atom, if it is another methyl group, it becomes more difficult. If one more methyl group comes, it will be more difficult. If one more methyl group comes, it will be much more difficult for the attack of nucleophile. Hence, in case of SN2, the lesser number of alkyl groups, it will be much more easy. So, what you have to remember in SN1, which is the order, it is tertiary, secondary, primary alkyl halide, which will be the order of reactivity. That means tertiary alkyl halide will undergo reaction faster. In SN2, it will be primary, secondary and tertiary. So, I hope it is clear. So, here we have taken the example of an alkyl halide. As you can see, 3 hydrogen atoms are here and you have your halogen. This is the SN2 mechanism which is shown here. The nucleophile will attach from this side. Okay. So, in this case, it will be easier because all the 3 are hydrogen atoms. Now, instead of this hydrogen, you have a CH3 group here. So, it becomes more difficult. And you have one CH3 and you have another CH3 also instead of hydrogen. So, it becomes more difficult for the attachment or attacking of nucleophile, and in here you can see all the 3 are CH3. So, what happens? It becomes more difficult. So, this order of reactivity is very important. In SN1, it is tertiary, secondary, primary, and in SN2, it is primary, secondary, tertiary alkyl halide, right? Okay. So, what is exactly primary? This is an example of primary because this particular carbon atom is not further attached to any other carbon atom. Here also it is a primary carbon. So, this is also a primary alkyl halide. Why? It is only further attached to one carbon atom. Now, this is a secondary alkyl halide because this carbon atom is attached to this carbon atom as well as this carbon atom. Okay. So, now it is tertiary. This one is tertiary because the carbon atom which is attached to the halogen is attached to 1, 2, 3. Further 3 carbon atoms. So, based on the carbon atom which is forming the bond with halogen, that carbon atom is further attached to how many other carbon atoms. Based on that, we can say primary, secondary, tertiary. So, this is the carbon atom which is attached to the halogen, right? This carbon atom. This is attached to only 1. So, it is primary. This is attached to 2. So, it is tertiary. This is attached to 3. So, it is tertiary. Okay. So, this is primary, secondary, tertiary. So, this will be the order. So, this order is very, very important to remember. Okay. So, the order of reactivity of alkyl halides towards SN1 and SN2. Okay. So, we have already discussed this tertiary, secondary and primary, and this is the methyl halide. Okay. that is CH3Cl, CH3Br, any one. Okay, there is no other carbon atoms. Okay, that is why that comes in the last. So all this, if we are considering, this will be the order for SN2. We have already discussed. Tertiary will be the one with having the least reactivity. Highest will be for your methyl halide. Now SN1, the highest will be shown by tertiary halide. Okay, so I hope substitution nucleophilic reaction is clear for you. That is SN1 and SN2 mechanism, the order of it, the kinetics, the stereochemical aspects of it, everything is clear for you. So in the next session, we are going to study elimination reaction. We have discussed substitution nucleophilic reaction, right? So in the next session, we are going to study elimination reaction of haloalkanes. So I hope the concepts that we have covered in this session is clear for you. So that's all for today. Thank you.